Hi, I'm Professor Goins and welcome to the Math Professor's YouTube channel. If you're looking for videos explaining topics in mathematics ranging from algebra on up, please consider subscribing and checking out our playlists, videos, liking, commenting, sharing, all those things are greatly appreciated. So let's go ahead and get into the current video. What I want to take a look at is what is a topological space. And this is one of those topics that you'll learn in probably a senior level undergrad, maybe beginning graduate school, but it's right about that level. Now, if you're getting into a course called topology, you've probably studied linear algebra, and where you talked about what is a vector space. You possibly have taken a look at an abstract algebra course where you looked at groups, rings, fields, probably not modules yet, but you've seen examples of a set with an operation. So in other words, you've got a set with something else, a set with certain requirements. Okay, so that's what you see in those other sort of algebraic structures. Well, a topological space is another type of a structure where it's going to be a set with something else with it. And this video isn't going to necessarily give you a really good feel for what a topological space is, but we're going to go through the definition. I'll give you some examples of what is a topology, what isn't a topology, things like that. But you really won't get a good feel for what a topological space is until you spend time working examples and writing proofs and learning more material related to topological spaces. Initially, it's basically a way to sort of abstract some of the concepts that you talk about in a calculus or more appropriately an analysis course. For example, the concept of continuity, openness, closedness, things like that. We will sort of generalize those in the context of a topological space. So let's go ahead and get to the definition. Definition. For a set, so for a set X, a topology on X, labeled tau, traditionally labeled with the Greek letter tau, is a collection of subsets of X for which the following properties hold. So tau is a subset of the power set of X. It has to be a collection of subsets of X for which the following three properties hold. 1, the empty set and X, which of course are subsets of X, must be in the collection tau. 2, if I take, so let me say this before I write it, I can take any arbitrary collection of elements of tau, whether it's a finite collection, a countable collection, uncountable collection. I can take any amount of elements of tau, take their union. The union must also be an element of tau. Written symbolically, this says for any collection of subsets of tau. So if ui is an element of tau, the collection of those would be a subset of tau. So for any arbitrary subcollection of tau, their union must be an element of tau. Tau contains arbitrary unions of its elements, 3. So let me say this before I write it. If I take any finite collection of elements of tau, which is any finite collection of elements of tau, those are also subsets of X, their intersection must be contained in tau. So tau must contain arbitrary unions and finite intersections. So written symbolically, this says for any finite collection that is a subset of tau, the intersection must be contained in tau. Okay? Now, a set X along with a topology tau, sometimes written as the pair x tau, is a topological space. So a topological space consists of two things. It's a set with this collection tau, which is a collection of subsets. In other words, it's sort of like a group, right? In that it's a set along with more information. Okay, same thing with a ring. Okay, it's a set with more information. Now, the elements of tau are called open sets. Okay. Certainly, if you're watching this video, you've taken, probably an analysis course, but at least some calculus courses, and you know open intervals on the real line. You're familiar with the word open sets. Well, we can abstract that concept quite a bit, and open set doesn't necessarily have to mean an open interval on the real line. It can mean lots of other things as well, but elements of the topology are called open sets, and then also a set W is closed if its complement is open. Okay, so we've got open sets and closed sets. Okay. Well, again, this definition is pretty abstract, so let's go ahead and let's take a look at some concrete examples of topological spaces, and in particular, some examples where I'm going to show you for a set something that is a topology, something that is not a topology. And they're going to look fairly similar, but of course the one that's not a topology is just not going to satisfy all of the requirements. So let's go ahead and get rid of all of this stuff. For example, let's start with a set that has three elements. Let's say the set X consists of A, B, and C. Okay, set X consists of A, B, C. Now, I'm going to use Greek letter alpha here, and alpha is going to be the following subcollection of subsets, or the following collection of subsets of X. It's going to consist of the empty set, the singleton A, the singleton B, and the set consisting of BC. Okay. Now take a look at that collection. Notice all of these are subsets of X. To determine if it's a topology, we have to check the requirements that I had a few moments ago. Well, let's see. Very first thing that I had listed contains the empty set. It sure does, but it does not contain the entire set X. So therefore, this is not a topology. Okay, so it's definitely not a topology. But what else? What other requirements does it fail? Well, if I take the union of A with BC, that would give me ABC. That's the entire set X. That's not in there, so it doesn't contain unions. Intersections. Well, if I take the intersection between A and BC, I get the empty set. If I take the intersection between B and BC, that would be the singleton B. So it does contain intersections, but it does not contain unions, and it does not contain the entire set X. Therefore, again, that is not a topology. How about this one, tau 1? How about it contains just the empty set and the entire set X? Well, first requirement, of course, is trivially satisfied. Moreover, if I look at unions, union of any collection of the empty set and X is either going to be the empty set or X, so therefore that's satisfied. Arbitrary or countable, finite intersections will be satisfied as well, because again, I'm only going to get the empty set or X out of those two. This one is sort of like the smallest possible topology, and therefore this is given a name. This is called the trivial topology. So not a particularly interesting example, but a lot of times in mathematics, no matter what the concept is, we like to look at the extremes of what's the smallest or the biggest or the most that we can get out of something. So again, tau 1 is the trivial topology. Tau 2, all right, let's say I've got the empty set. Let's say I've got the set containing A, set containing B, and the set containing AB along with X itself. So you can go through and you can verify, but notice that this is in fact a topology. If I take any unions, well, this contain the empty set and X, got that. Unions, A and B gives me AB, AB with X gives me X, X with A gives me X, empty set with A gives A, right? So it contains unions, contains intersections. So if I take B with the set AB, I get B, A with AB, I get A, X with B, I would get B, so on and so forth. So this, in fact, is a topology on the set X. Tau 3, let's just do one more example. Well, remember that a topology consists of subsets of X, right? Well, what if I said the topology tau 3 or the collection tau 3 consists of every single possible subset of X? In other words, the power set of X. Okay. Well, this is the other extreme from the trivial topology, where this is like as small as possible, and the tau 3 in this case would be as big as possible. And this one also has a name called the discrete topology. So between all three of those topologies that I have on the set X, we can actually construct three different topological spaces: X tau 1, X tau 2, X tau 3 are all topological spaces, and they're all different. Again, I'm not going to really get into that here in this video, but when we start talking about functions between topological spaces, the notion of continuity, for example, is going to be different between those three, okay, even if it's the same function. All right, let's go ahead and take a look at one more example. So let X be a set and define tau to be the following collection. The collection U, so the sets consist of U, where first and foremost U is a subset of X, okay? And if I take the set complement X minus U is either finite or all of X. So in other words, what I'm saying is a set is open if its complement has finitely many elements, or its complement is all of X. Let's take a look at verifying that this is a topology. So verify that tau is a topology on X. By the way, again, so this is going to be a topology. I'm going to verify in the following solution. This is actually a very famous example that you'll see in probably no matter what topology textbook, as long as it's sort of like an intro textbook, like a more advanced book probably might not have this example. But pretty much any introductory topology textbook is going to have this, and this is called the finite complement topology. And it is a pretty abstract concept, but I think it's a really good example of just illustrating and working with the definitions. Okay, so tau consists of the sets where its complement is either finite or all of x. Well, notice x minus the empty set, right? The set difference of x minus the empty set is the set x itself. Therefore, the empty set is an element of tau, right? Remember that the elements u are the part of the set difference that I'm subtracting off of x, right? So therefore, this empty set is in there because the set difference is all of x. Also, if I take the set difference of x with itself, that's the empty set. And of course, the empty set has 0 elements, so in other words, a finite number of elements. And that implies that the set x itself is an element of tau. Okay. So far the collection tau consists of the empty set and the set x. So it's, in particular, it's non-empty. So now let ui, where I is ranging over some arbitrary index set, is a collection of subsets of x. In other words, that's a collection within tau. Now what I want to do is I need to determine if x minus the arbitrary union if this set right here is either finite or all of x. Okay? Well, let's see. Remember, if I take x minus a union, that's actually going to be the intersection of x minus ui. Now, each x minus ui is a finite set. Each one of these, because ui is an element of tau, therefore each one of these is a finite set. And so in particular, if I choose a specific I value, this would be properly contained, or at least it'd be a subset of, let's just say, ui1, where I1 is an element of I. Well, this is a finite set, and this is contained in it. Therefore, this right here must be a finite set. Therefore, x minus the complement must be a finite set, and that implies that the union, where I ranges over the entire index set I, is an element of the topology. Okay. Similarly, let vi, where I equals 1 to n, be a finite collection of tau. Okay? So again, that means that the complement of each one of these is in the set. And so what I need to do is determine if the intersection of all the vi of those vi's is an element. So what I'm going to do, my test, is I'm going to take x minus the intersection from I equals 1 to n of vi, okay? Because if this set is finite, then that means that this set, the intersection, is in the element of is in the topology. Well, if I take the complement of an intersection is a union, so that'd be the union from I equals 1 to n of x minus vi. Now remember that x minus vi is finite for every I, and 1 to n, this is a finite union. So a finite union of a finite collection is also a finite set. Therefore, the complement of this is finite, which implies that the intersection is an element of the topology. And therefore, the finite complement topology is, in fact, a topology. Okay. Thank you for watching, and please consider subscribing and looking forward to more topology videos.